having a look at this problem here, okay, so remember this is all on page 6 of the formula booklet, and you've got the formulas given to you for SXX, SYY and SXY. It's pretty much plug and play, plugging the values in and getting a value out. Make sure that you show the steps that are needed, so that you're not just trying to put it all into the calculator in one go, okay? Not only are you potentially going to lose out on any kind of method marks, but if you make one little slip on your calculator, then bye-bye all the marks, okay, for that question. So you've got to be thinking carefully about not cutting corners with S2, okay, which some of us can be prone to do if we're not careful, right? Not pointing any fingers. Right, so results from this, SXX 356.1, SYY 702, SXY is minus 462, and then substituting them in. This is what I would probably suggest you actually writing down in the exam, okay? So actually having the individual values and showing them being substituted in, okay? Right, so what we're going to be looking at today is building on this concept, but we're going to be reintroducing an old favourite from S1, and that's hypothesis testing, okay? It's one of 4 different hypothesis tests that we could be asked to work with in an exam for S2. So there are always going to be little subtleties that we need to be aware of and keep up to date with, okay? So the first thing that we really need to talk about is what we mean by a sample correlation coefficient, okay? Now, in the grand scheme of things, if you were actually trying to determine whether there was some kind of correlation between 2 variables, and you go out and collect the data, really that data that you have is only a sample of a much greater and wider population, okay? So it's only a sample of a larger section, so you've only done a little bit of it, okay? Now, if you find that in your sample you've found that the value of R, your product moment correlation coefficient, is close to 1 or minus 1, then you are probably going to be reasonably satisfied that the 2 must be linked in some way. Now, we know from before, right, from last lesson, that correlation does not imply causation. Good, right? So we know that from before. However, if we've got quite a strong value of R, so like 0.999 or something like that, then we could be kind of on the verge of thinking that there is some kind of link between the 2. Or at least, not necessarily a link between the variables, but at least there is a positive correlation or negative correlation. If, however, you found that the value of R is not close to 1 or minus 1 and might be around about 0.6, then we need to do a little bit more thought, okay? So when we talk about a bivariate distribution, okay, bivariate just means 2 variable, okay? So bi meaning 2, variable, okay, so 2 variable distribution, the fact that it was you've got an x and a y, okay? So this might be the parent population, okay? And what you've got is a sample. So we've got these separate ones circled, okay? These bits of data are in the sample. They're the ones that you've collected, and you've calculated this product moment correlation coefficient of 0.6. It's not particularly strong, so we need to think a little bit more about what we can say about the data itself. So that's when a hypothesis test comes in. We're trying to determine if the value of R that we're getting is strong enough and unusual enough, significant enough, you know, word dropping there, right? Significant enough that we could then infer something about the parent population, okay? Because I'm getting a very strong correlation for the sample, does that mean I'm getting a very strong correlation for the parent population? That's what we need to think about. So, the parent population, there will be a correlation attributed to that, and we refer to that using the Greek letter rho. Okay, so instead of R, R's the sample one, rho is the parent one. Okay, so we're going to have R for the sample and rho for the parent population. Okay. Now, we could use the value of R that we've got as an estimate for rho, and although this isn't the only hypothesis test that we could do, but one hypothesis test, and the one that we work with for this section, is to consider the null hypothesis. So remember, that's the devil's advocate position, to say that the parent population has no correlation. Okay, and we're going to determine if having some form of correlation for the sample will infer otherwise. Okay, so that's the kind of rundown, that's the idea. Now, something very important coming up next. Actually, could you see if you could tell the person next to you what you understand by the significance level of a hypothesis test? What was all that about? Go on then, Aaron.
It's the percentage chance of you falsely discarding the null hypothesis.
The percentage chance of falsely discarding the null hypothesis. That's pretty good, isn't it, right? So, in other words, if you've got a 10% significance level, then you've got a 10% chance of rejecting the null hypothesis when in fact it's correct. Okay? That's the idea. So, once again, one important thing to write down for today, okay, is that the significance level is the probability of rejecting the null hypothesis when in fact it is true. Okay? That's something that I would definitely suggest you memorize. The second bullet point also is incredibly important. The hypothesis test will only be valid if the underlying parent population is bivariate normal. Now, at the moment, we haven't met the normal distribution. Okay? We haven't done that yet. However, so that you kind of have an idea of what the normal distribution is, as you kind of copy those bits down, what the normal distribution will be all about is a symmetric bell curve, where you can kind of imagine that, let's say you have the heights of trees, for example, of a certain kind of like type of tree, and you're going to have a lot that are in the middle. Okay? Then you're going to have some that are quite tall, but there's going to be fewer of those, and fewer that are going to be quite short. And we're talking about kind of like if they're all the same age, to be fair. Okay, so you have some that are going to be quite tall, taller than the rest. Some that are going to be quite small, but the majority are going to be somewhere in the middle, you would assume. Okay, a lot of continuous bits of data are normally distributed, or you'd expect to be normally distributed. You've got a lot in the middle, you've got some at the top end, some at the bottom end. Okay, it makes sense to be that way. Not all populations are going to be normally distributed. Okay, but in order for this to work, okay, for this to be valid, we assume, we would hope that the underlying population is bivariate normal. Okay. You could potentially be asked, is the population that's described likely to be normal or bivariate normal? Okay, so that may well be something that crops up. Okay, so how do we deal with this hypothesis test then? So we know that the null hypothesis, that devil's advocate position, would say that there is no correlation between the two variables. Okay, so this is what we would be working from. The null hypothesis, H0, is where rho is 0. And we've got three possible routes through. Okay, you've either got that there is some correlation between the two. So that would mean that rho's not 0. Okay? That will give you a two-tailed test. You could have that rho is positive, so there is some positive correlation between the two, or that there is less than 0, and so you'd have a negative correlation between the two. So kind of very similar in kind of idea to what you did last year with binomial hypothesis testing. It's not too different. Okay. So what we're going to do is we're going to jump straight into an example. Okay. So the example we're going to have a look at is this. And we'll see if we can build up the idea. Right, so data is collected from 6 students to determine whether there is a correlation between their IQ and the number of hours they spent the previous week watching TV. So we've recorded the number of hours watching TV and their IQ from some IQ test. We want to conduct a hypothesis test at the 5% significance level to determine whether watching TV has reduced the student's IQ. Okay? Now, very briefly, would we expect these two variables to be normally distributed? Would we expect there to be the majority in the middle, some at the lower end, a few at the lower end, few at the top end?
Yes.
Yeah? So number of hours TV watched, then most of us are probably going to be around the same amount. Some of us are going to be TV kind of addicts, kind of like sitting there watching it for hours and hours and hours. Some of us might not watch any TV at all. Okay? IQ, probably the majority is going to be around the middle, some higher, some lower. Okay? You could kind of imagine it. Right. So how do we go about this then? First step. Can you remember how a hypothesis test in S1 always began? It always began with one sentence. It's been a while, hasn't it? Let P be the probability of yada, 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 right? So it always started with that first sentence. We've got a first sentence of our own, okay? But it's always the same and not in context, which is good. So this always starts with precisely the same sentence. Okay? Let rho be the population correlation coefficient. Nice and straightforward. the null hypothesis is also always the same. So rho is 0. So what we would be saying there is that there is no correlation between IQ and watching TV. That's the null hypothesis. Now, what we're thinking in this problem is that watching TV will have a negative impact upon the student's IQ. So the alternative hypothesis would be to say that there is some negative correlation between the two. And so what we're actually looking at is a one-tail test here. Okay? Right. Now, we need a value to compare against. Okay? So last year you would have used the statistical tables, right? So what we're going to use is, once again, the stats tables, okay? We've got 6 students. So n equals 6, 6 students, 5% significance level. What we get is a critical value. Okay? Right. Formula booklets. Where are we? On the right page? Not on the right page. Oh, there we are. Page 21. Page 21. What you'll see on the left-hand side of page 21 are critical values for the product moment correlation coefficient R. You will have a one-tail test, two-tail test at the top of these bars. We are on a one-tail test at 5%, so furthest left, and then you're going down to n equals 6, and you should get 0.7293. Okay? So that's got our critical value. But we haven't got anything to compare it against. Oh no. So, so what we're going to need to do is to find the product moment correlation coefficient for our sample. We need to find a value of R. Okay? So on your calculators, could you find me the value of R? Right, I believe, right, you should get value of R to be minus 0.425. Okay? Now, how do we interpret this? Okay? Now, what you've got to imagine, because our value is, I'll write that down, minus 0.425. Okay? So what you've got to imagine is that we've got this number line going from minus 1 up to 1. Okay? We know that these values of R go between minus 1 and 1. We've got 0 there. Okay, and we've just calculated that our value is minus 0.425, so somewhere around about there. Okay. Now, the critical value that you get, this 0.7293, do you notice that in your tables, okay, when you look at the tables, there are no negative values in there? Okay. There are no negative values in there for the population correlation coefficient, right? For the critical values. So what actually how you use it is that the 0.7293, they're not just over here, but you can also interpret it using the negative of it over here. Okay, so our critical value is actually here at the minus 0.7293. Okay, so what we're finding is actually that our value of R is there, so it's kind of outside what we would be referring to as the outside of being significant. Okay, so because we're finding that minus 0.425 is greater than minus 0.7293, okay, it's not significant. So not significant. So we fail to reject the null hypothesis. Okay? So remember, now, I know I've copied a bit from a book here that says accept H0. Now, by all rights, and the correct way of interpreting hypothesis tests, you shouldn't really accept H0 because that kind of gives some acceptance to assuming that H0 is therefore correct, when in fact we haven't gathered enough evidence to suggest otherwise. So instead of really accepting, really you should say failing to reject. The likelihood of you being knocked down a mark for that is very slim indeed. Okay. So we're failing to reject H0, so we must have a final concluding statement, as was always the case last year, okay? So there is insufficient evidence to suggest, so it must have these kind of, it mustn't be for definite, okay? We haven't gathered enough evidence to suggest that watching TV, to suggest that there is a negative correlation between IQ and watching TV. So it should be in context. It should talk about the correlation, okay? The fact that you're either looking at it either positive, negative, or in two-tailed test as no correlation. Okay? So that is how we deal with a hypothesis test for Pearson's coefficient.